It's almost time to fly a helicopter, but before we get to fly a helicopter, we need to learn a little bit about what's going to make this thing fly. Some people think just get a big enough fan attached to your car, be a helicopter you can lift up. Well, get a big enough fan, I don't think your car is going to fly. So it's going to need something else. Now, we have 4 aerodynamic forces. We have lift, weight, thrust, and drag. So lift is going to have to overcome the weight of the object that it's trying to lift. In our case, our helicopter. Thrust, to move it forward, is going to have to overcome drag, trying to keep the helicopter backwards. Then we have the lift equation. The scientific equation is that lift is equal to the coefficient of lift times 1/2 the air density times the velocity squared of the airfoil times the surface area of the airfoil. So this equation includes things we can both control and some that we can't control. But wait, you say, isn't that the same lift equation that airplanes use? This is a helicopter. True, lift is lift, and helicopters, they're also known as rotor wing aircraft. The rotor blade of the aircraft is an airfoil, having the same shape as an airplane wing. But instead of rolling down the runway at 100 miles an hour, we're going to speed up the rotor blade to a few hundred miles an hour and take off vertically. But still, not quite that simple. So back to the lift equation, and things we can control and some we can't control. First one, coefficient of lift, which for the pilot relates directly to angle of attack, which relates directly to the pitch angle of the blade. Further dumbing it down, it's going to be how much the collective lever is pulled up by the pilot inside the cockpit. On our helicopter, the rotor blade is symmetrical airfoil, meaning that when the collectives fold down, the coefficient of lift is 0. So speed that blade up as much as you want, but the helicopter, it's not going anywhere. It's not going to take off. So as the pilot raises the collective lever inside the cockpit, the pitch of the rotor blades is increased, which also gives an increased angle of attack and increased coefficient of lift. Next part of the equation is something we can't control, which is air density. Luckily for us, we're here in New Orleans, where part of the city is below sea level. So the air density really can't get much higher than it is. Then we have velocity squared. Here's where things start to get different from airplanes. For the lift equation, it's going to be the velocity of the airfoil. On the R-44 helicopter behind me, the tip of that main rotor blade travels through the air at approximately 480 miles an hour. Add some forward airspeed, things get even a little trickier. So velocity is something we have some control over, but only in a limited fashion. In the helicopter, the rotor blade at flight RPM is going to be a constant RPM. If we lose some of the RPM, we can add a little more throttle to bring it back up, but it's just very limited control over that tip speed. We can't go and say double the speed of the rotor tip blades, 960 miles an hour, to get more lift. If we tried to do that, we'd have a lot of problems. However, moving the helicopter forward over the ground, increasing some airspeed, is going to add that velocity onto the top of the velocity of the rotor blades, albeit only in half the rotor disc. Lastly, we have surface area of the airfoil, which for us is going to be surface area of the rotor blades, and we can't change the size of those rotor blades. So how are we going to get in the air? We're going to need an airfoil, we're going to need a surface area, it's going to have some velocity, and we're going to have some air density, as in we can't do this in space, we need to do it here on Earth. And that airfoil is going to have some appropriate coefficient of lift. Combine these things together, we need to be able to produce enough lift to overcome the weight of the object we are trying to lift. So your model RC helicopter can run off a very tiny electric motor, but the larger the helicopter, the larger the engine needed to power everything to create enough lift to overcome the weight of the helicopter and of all the occupants. At this point, you might be thinking, I just want to fly, and we haven't even gotten to the symmetry of lift, translating tendency, translation lift, effective translation lift, torque effect, gyroscopic precession, induced flow, ground effect, just to name a few things that are a little important for helicopter flight. But back to the basics. In order to fly, you're going to need lift, and lift is going to need to overcome the weight of the object you're trying to lift. Moving forward, you're going to need thrust, and that thrust is going to need to overcome drag. In a helicopter, thrust is created by stealing a little bit of the vertical lift component, tilting it to create a thrust vector in the direction that you want to travel. So how am I going to fly this helicopter? We got some basic controls. They are the collective, the cyclic, anti-torque pedals, and the throttle. The collective is this lever on my left hand. What does it do? I raise it up and the helicopter goes up. Push it down and the helicopter comes back down. Cyclic is going to move the helicopter forward. Push it forward, helicopter moves forward, backwards, helicopter flies backwards, sidewards, in the direction I want to travel. It does that by changing where lift is created in the rotor disc, thus tilting the rotor disc in a particular direction and pulling the helicopter along with it. Then I got these anti-torque pedals here at my feet, and that's going to control the thrust created by the tail rotor. The tail rotor is one of our biggest friends in flight, keeping us from getting extremely dizzy. With no tail rotor, the helicopter will just spin constantly in the opposite direction of the main rotor. The anti-torque pedals are controlling the pitch of the tail rotor blades and controlling how much thrust is being created, and thus controlling if the helicopter will turn around the mast, either to the right or to the left, or not at all. If I want to nose the helicopter to turn right, I press more right pedal. If I want to move to the left, I give more left pedal. Now, this is all within an aerodynamic environment, so there's no set amounts of 1 inch this, 1 inch that. In flight, you have to find the equilibrium, and from that point, it is either right or left. Then we got throttle, and we're not going anywhere unless these rotor blades begin to spin. However, I did mention that in flight, the rotor blades are kept at a constant RPM. The throttle lets us set the engine RPM, which is then going to be connected to the rotor RPM. We use the throttle in startup as we go through our checks. However, in flight, the governor automatically keeps the RPM at its flight RPM.